Hi, I'm going to show you how to solve this problem with a visual representation of the recursion. If you haven't already solved is_same_tree, which is problem 100 on LeetCode, please do so because we use that exact algorithm inside of this one to solve it. Let's talk about the problem really quick. Problem 572, subtree of another tree. Like I said earlier, first thing is we declare is_same_tree. It's the same algorithm. And below that, we're actually doing three if statements. So this is the first thing that happens inside of our is subtree algorithm. We're checking if there isn't a subroot. If there isn't a subroot, if this is null, we return true because at some point in our root, there is going to be a null node, which means it's true. It's a subtree or a subroot. The second if statement checks if there is no root and there is a subroot. That would mean it's impossible to have a subroot on a root that doesn't have anything, so we just return false. The last if statement checks if is_same_tree returns true. If it does, we return true immediately right here. If it doesn't return true, we go down here and we call is_subtree recursively. And keep in mind, we're always entering subroot as is. We're not incrementing through it because that's what we need to check against the new root node. In this case, it would be the new root node becomes 4. It's root.left, okay? And in this case, it's the new root node becomes root.right, which is 5. Now, a cool thing about this is we're using the logical OR operator, which will return true as soon as it finds a true condition. So as soon as we find one of these is true, it passes that up and just keeps recursively returning true. So it will stop essentially as soon as we find one of these is true. Whereas is_same_tree uses the logical AND operator, which will return false immediately as soon as it finds a false condition. So for example, as soon as it checks 3 against 4, it hits this check, root.val does not equal root.val, right? And it returns false immediately, which makes this entire algorithm efficient. We're looking, as soon as we find the conditions we need, it returns up. Where it's not efficient is if there is no conditions, it will just go through the entire thing. In this situation, we go through every single node and we just return false, false. So our time complexity is root times subroot, because that's the maximum number of operations that we would do. Our space complexity is the minimum between root and subroots. A brief walkthrough looks like this. We call is_subtree on root and subroot. Then we carry out these three if statements. The last one causes us to call is_same_tree on root and subroot. One of the if statements in is_same_tree checks the vals of both these nodes. They're not the same, so we return false. Then we call is_subtree on root.left and subroots. And that causes us, again, to check these three if statements. The last one causes us to call is_same_tree on root and subroot. Remember, this has been changed to root.left here. And we check all of the nodes inside of these two. And that would look something like this. 1, 2, 3, 2, 4, 2, 1, 5, 6, 5, 7, 5, 1, true, return true, up, true, 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 finished. A more detailed explanation looks like this. First, we call is_subtree on root and subroot. In this example, those are 3 and 4, here and here. So then we carry out these three if statements. None of them hit, but in doing that, we check is_same_tree for root and subroot, and we check these two values. They're not the same, so we return false, which means we get to here and we call is_subtree on root.left and subroot. Root.left from here is 4, so we call it 4 and 4. This is subroot. Then we check these three if statements. These two don't hit again, and then we hit is_same_tree on root and subroot. In this case, it's 4 and 4. We check, are these the same? In this case, they are exactly the same, so we return true up, which puts a true on one side of our logical OR operator, which means we can immediately return true up to our root, and that's all.